Okay, we can have a look at, let's use red. We can have a look at example 210, motion at constant velocity. So this is part of section 2.8. So we already saw in 2.7 and 2.8 that we have velocity given by delta x over delta t, which is the same as final position minus initial position over final time minus initial time. Okay, so, and we saw basically that if you've got a position time curve and you want to construct the velocity time curve, what you need to do is you need to find what the slope is of that curve. And in this case, we saw that it's a positive constant slope, and so it'll look something like that, velocity time. And then we also saw if I have the velocity time curve and I want to find what the change in my position is, I need to calculate the area under the curve over a certain time span. So if I have an initial position at t equals 1, if I have an initial position at time 1, and I want to find what is my final position, I need to calculate the area under the curve. That area under the curve is equal to the change in my position. Okay, now let's have a quick look at this example here. Figure 230 shows a position time curve, and the object is moving at constant velocity. Do you guys see that? Why is it constant velocity? How can you tell? Because the slope is constant. So question A is, what is the x component of the object's velocity? So we know velocity is given by delta x over delta t. So it's up to you, but you can choose any delta x and its corresponding delta t. What they do is they choose this entire delta x here, right from this point to that point, and that's delta x equal to 5.2. This is 5.2 here plus 5.2, and this is 1.6. So delta x is 5.2 minus 1.6, and the entire time is 6 seconds. So you get 3.6 over 6, and you get your velocity is a constant plus 0.6 meters per second. Now, you could actually have chosen anything else. So you could have chosen the time span between 0 and 2, for example. Then you would have had this little triangle there, and so that would have been your delta x for your calculation of your slope, and that would have been your delta t. You could have chosen between 2 and 4, you could have chosen between 4 and 6, you could have chosen anything as long as you could calculate the slope. Alright, so that's the velocity. The velocity is the slope, the gradient. B says write an expression for x of t. So this is just a curve, but what is the actual function x of t as a mathematical expression? Well, we've already got the slope. Okay, we've got the slope. Now we need to know, so x of t, we've already got the slope, which is 0.6 times time. But as you can see, the intercept is not through the 0. If this line looked like this, right, then that would have been our solution. But you can see the intercept is not through the origin, it is through something there. So the answer then is at time equals 0, what is my position? My position is 1.6. So the answer is 0.6t plus 1.6. That is my position, my xt function. This is the actual mathematical function of that slope. Okay, so there it is. X of t. X is a function of time. So that's my position time function. What is question C? What is the x coordinate of the object's position at time equals 25 seconds. So we don't have 25 seconds here on the curve, but now we've got a function. So we can just take that function and plug in the time over there, and we get a position, the x-coordinate of the object's position. Okay? How would you draw this as a velocity time? That's my own question. Well, if that's your velocity time curve, all you need to do is differentiate this. Get the slope of this. Get the slope of this. And we see that the slope is 0.6. So you would have a constant velocity of 0.6 meters per second. Okay, see you in the next video.